Welcome to Electronic Seed YouTube channel. Today in this video, we will learn about noise rejection in analog and digital signals. Let's get started. Every communication system faces a constant threat from noise that can disrupt the integrity of our signals. Noise can come from many places like electromagnetic radiation, your power supplies, or even adjacent signal lines. With analog signals, noise gets permanently embedded into the waveform, which means you cannot recover the original clean signal. Digital signals, however, use discrete voltage levels that allow them to reject low-level noise quite effectively. In this article, we'll explore exactly how that noise rejection works, along with its limitations. First, we'll go over the fundamentals of signal, noise, and voltage. Then we'll look at analog transmission, which uses continuous values and leads to permanent distortion. After that, digital transmission, focusing on discrete levels and noise margins. We'll walk through a step-by-step explanation of how digital noise rejection actually works. Next, we discuss the limitations of basic digital noise rejection. Then we'll look at practical applications and real-world industry examples. And finally, we'll wrap up with a conclusion. A signal is simply a time-varying voltage or current that carries information from one point to another. Noise, on the other hand, is an unwanted random fluctuation that gets added to the signal during transmission. The channel could be a copper wire, a trace on a printed circuit board, or even a wireless link. The fundamental challenge is that the receiver cannot easily tell the original signal apart from the added noise. Analog signals represent information using continuously variable voltage levels. For example, a pressure sensor might output 0 to 10 volts to represent 0 to 100 psi. In analog systems, any voltage within that range is considered a valid and meaningful value. Imagine a transmitter sends 3.6 volts, but noise adds 0.4 volts. The receiver sees 4.0 volts and interprets that as the correct value, even though it's wrong. The original 3.6 volts of information is permanently lost. So the error is exactly equal to the full noise amplitude, in this case, 0.4 volts. Digital signals use a finite set of allowed voltage levels instead of a continuous range. In a simple binary system, 0 volts might represent logic 0 and 5 volts logic 1. For multi-level signaling, consider 0 to 8 volts with 4 levels, giving a step size of 2 volts. The allowed levels would be 0, 2, 4, 6, and 8 volts, each representing 2 bits of data. Suppose the transmitter sends 4 volts for the binary bits 1, 0, and noise adds 1.5 volts. The receiver sees 5.5 volts, and the nearest valid level is 6 volts. This results in a digital error, meaning an incorrect interpretation of the bits. Using the same system, now transmit 4 volts and add a smaller noise of 0.8 volts. The received voltage is 4.8 volts. The distance to the correct level of 4 volts is 0.8, while to 6 volts it's 1.2. So the receiver correctly outputs 4 volts. The noise of 0.8 volts is rejected because it's below half the step size. The noise margin is step size divided by 2, which is 1 volt in this example. Step 1. Define a set of discrete voltage levels between your minimum and maximum voltage. Step size equals the voltage range divided by the number of levels. Step 2. Assign decision boundaries at the midpoints between adjacent levels. Step 3. The transmitter outputs a precise voltage corresponding to the digital value it wants to send. Step 4. The communication channel adds unpredictable noise voltage to the signal. Step 5. The receiver measures the voltage and picks the valid level associated with that region. Step 6. Noise is successfully rejected if the absolute noise is less than half the step size. Step 7. The maximum correctable noise, also called the noise margin, is exactly step size divided by 2. For example, 0 to 8 volts with 4 levels gives a step of 2 volts and a margin of 1 volt. So noise of 0.9 volts is rejected, but noise of 1.1 volts would cause an error. Simple quantization fails as soon as the noise exceeds half the step size. For instance, transmitting 4 volts with noise of 1.2 gives a received 5.2 volts. The nearest level is 6 volts at distance, 0.8, instead of 4 volts at 1.2, so we get an error. One solution is to increase the number of levels, which also increases data rate. But the trade-off is that a smaller step size actually reduces the noise margin. Another solution is to use error-correcting codes that can detect and fix bit flips. Solution 3, differential signaling, which cancels out common mode noise. Solution 4, shielding and filtering the signal before quantization. Large noise, like 1.3 volts in a system with a 1.25 volt step, will still produce a wrong value. Advanced methods include forward error correction, or FEC, and automatic repeat request, or a RQ, which asks for retransmission of corrupted data. In practice, real-world systems combine multiple of these techniques for better reliability. In industrial sensor networks, 4 to 20 milliamp loops help reject noise from motors. Audio interfaces like USB and HDMI use differential pairs to prevent ground loop noise. The automotive CAN bus uses dominant and recessive encoding to achieve high noise immunity. For microcontroller analog to digital converter inputs, we use internal comparators along with software averaging. To summarize, digital noise rejection relies on discrete voltage levels and decision boundaries. Analog transmission permanently includes noise in the signal, while digital systems have the ability to cancel it out. Any noise that stays below half the step size is completely eliminated by the receiver. That's why modern systems like USB, Wi-Fi, and fiber optics all prefer digital encoding. Engineers must carefully balance the number of levels and add error correction to handle large noise.